Hello everyone. I hope you all are good. So the topic that we are going to discuss today is electrostatic potential and capacitance, NEET PYQs. Disclaimer: the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the content immediately. Please note that the parts of the content may have been generated using generative AI, which is experimental. So our first question: a parallel plate capacitor is made of two dielectric blocks in series. One of the block has thickness d1 and a dielectric constant k1, and other has thickness d2 and dielectric constant k2, as shown in the figure. This arrangement can be thought as a dielectric slab of thickness d, which is equal to d1 plus d2. d1 is the thickness of the first dielectric k1 and d2 is the thickness of second dielectric k2, and effective dielectric constant k. The k is, you have to find the effective dielectric constant. The options are k1 d1 plus k2 d2 upon d1 plus d2. B option is k1 d1 plus k2 d2 upon k1 plus k2. C option is k1 k2 d1 plus d2 upon k1 d2 plus k2 d1, or D option is 2 k1 k2 upon k1 plus k2. So these are the four options given. So let's have a look that how can we solve this. Okay, so I will give you some time to think about it. Okay, let's see the correct option. The correct option is k1 k2 d1 plus d2 upon k1 d2 plus k2 d1. Okay, so let's see. Now these are two dielectric blocks that has been inserted between the plates of the capacitor, and thickness of the one dielectric is d1, second dielectric is d2, and the total separation between the capacitor plate is d1 plus d2. Means these two dielectrics collectively fill the all the separation between the capacitor plates. Okay, so now we can assume this one dielectric as a one capacitor and this second dielectric as second capacitor. Means we can assume this as one capacitor having d1 separation between its plates and k1 is the dielectric medium that is fully inserted between its plates, and another capacitor c2 having dielectric constant k2, and the separation between the plates is d2, and this dielectric is fully inserted between the second capacitor plates. Okay, so these capacitors are assumed to be in series, so we can assume this type of structure to solve it. Okay, let's see what is the solution. So the given capacitor is equivalent to two capacitors joined in series. Okay, so we can assume this type of structure: one capacitor and second capacitor. These are connected in series. Okay, so first capacitor is having K1 dielectric and D1 separation, and second capacitor having D2 separation and K2 dielectric. Okay, so this type of structure we can assume. So C1 equal to K1 epsilon naught A upon D1. So capacitance of first capacitor having K1 dielectric between its plates and separation between its plates is D1. So capacitance will be K1 epsilon naught A upon D1. So this is for the first capacitors. So capacitance for the second capacitor that we have assumed, that this capacitor, second capacitor. So capacitance for the second capacitor is K2 epsilon naught A upon D2. Okay. So what is the equivalent capacitance of these two capacitors in series? 1 by C equivalent equal to 1 by C plus 1 plus 1 by C2 equal to, what is C1? Put these values of C1 and C2. So D1 by K1 epsilon naught A plus D2 upon K2 epsilon naught A. So 1 by C equivalent is equal to D1 K2 plus K1 D2 upon epsilon naught A K1 K2. Okay. So now what we can do now? Now we will assume this as a whole capacitor 1. Okay, having two dielectric blocks, that is given. Now we will assume that. So C equivalent will be epsilon naught A K1 K2 upon D1 K2 plus K1 D1, which is K1 D2, which is marked as equation 1. Okay, but equivalent capacitance of one capacitor having two dielectric blocks of equivalent dielectric constant K and separation between its plates D1 plus D2. Okay, so now what we will assume that, now we will assume that is given in the question that it is one capacitor only having two dielectric blocks having equivalent capacitance K. We will assume that equivalent capacitance of these two dielectric will be K. Okay, and separation between the plates of the capacitor is D1 plus D2. Now the equivalent capacitance will be given as epsilon naught A K, where K is the equivalent capacitance due to these both dielectric blocks upon the total separation between the capacitors D1 plus D2. Mark it as equation 2. Okay, so how we are going in that direction? Firstly, we will assume that these are two capacitors in series. This is first capacitor, this is second capacitor. This first capacitor is having K1 dielectric and this two capacitor 2 having dielectric K2. Okay, and these two capacitors are connected in series. So we found the capacitance of both these capacitors, okay, that in series, and then we find the K equivalent, which comes out to be epsilon naught A K1 K2 D1 K2 plus K1 D2, and mark it as equation 1. After that, we assumed this as one capacitor. Okay, so this is one capacitor and having this two dielectric blocks having equivalent capacitance K and having separation between its plates D1 and plus D2. Mark it as equation 2. Now compare these two C equivalents. Okay, and find this K. What is this K? Okay, so after comparing both these equations 1 and 2, we will get K equal to K1 K2 D1 plus D2 D1 K2 plus K1 D2. Okay, after comparing and solving, we will get the value of equivalent capacitance. Okay. Okay, next question. If potential in volts in a region is expressed as Vxyz. Okay, so in a space or in a region, a potential is given as this equation: 6xy minus y plus 2yz. The electric field in Newton per coulomb at point 110 is. Okay, so this type of questions are very important. So potential is given in this equation: 6xy minus y plus 2yz. The electric field you have to find at point 110, means x equal to 1, y equal to 1 and z equal to 0. Okay, so you have to find at this point, and options are minus in bracket 6 I cap plus 5 j cap plus 2 k cap, minus in bracket 2 I cap plus 3 j cap plus k cap, minus in bracket 6 I cap plus 9 j cap plus k cap, minus in brackets 3 I cap plus 5 j cap plus 3 k cap. Okay, these are the four options. So I will give you some time. So how will you solve it? By using E equal to minus dV by dr. That is the relation between electric field and potential. Okay, so I will give you some time to think about it. So answer is A option, minus in bracket 6i cap 5j cap plus 2k cap. So what is the solution? Potential in region V is equal to 6xy minus y plus 2yz. This is given in the question. Okay. So as we know that the relation between the electric potential and electric field is E equal to minus dV by dr. Okay. So we have to differentiate it with respect of R. But in equation there is no R. Okay. What is R representing here? R is the position vector of any point in the space. Okay, when we are differentiating with respect to x, this R will become x if there is only one dimension. If we are differentiating, or we will assume this potential in 2 dimension, then this R can be x or y both. Okay, when we are analyzing this potential and finding the electric field in 3D, 3-dimensional space, then this R will be x or y or z. Okay, so this R is a position vector representing the position. If we are dealing with 1 dimension, this R will be x. Okay, so this is the common notation. Okay, so E equal to minus now this R for x coordinate. Okay, with respect to, we have to find this dV by dr, means we have to find first with respect to x, then with respect to y, with respect to z. Okay, so this R we have to find in 3 dimension. So with respect to x, with respect to y, with respect to z. So firstly, this dV by dx with respect to x, this is the value of electric field, and this is the x coordinate of electric field. Means we have to specify the electric field at a point. So when we are specifying the electric field at a point, means this point is in 3 dimension. So it will have 3 coordinates, x coordinate, y coordinate, z coordinate. Similarly, electric field will have x coordinate, y coordinate and z coordinate. Got it? So electric field, this is the x coordinate of electric field. Del V by del x. This sign del, this is partial differentiation. Okay, what is partial differentiation? I am coming to that. Okay, so del V by del x I cap. I cap is the unit vector for x coordinate. Okay, electric field is vector, so it can be shown in the form of unit vectors, directions. Okay, see, this is the magnitude of x component, this is the direction I cap. This is the magnitude of y component, del V by del y, and j cap is the coordinate of y axis. Del V by del z is the magnitude of z coordinate, and k cap is the z coordinate, direction of z coordinate, and this minus sign according to formula. Okay, so now del V by del x, we will solve it step by step or separately. Firstly this, secondly this, and after this. Okay, so del V by del x, so put the value of V. Del by del x V, value of V is 6xy minus y plus 2yz. Now what is the meaning of partial differentiation? Partial differentiation means you are differentiating partially with respect to x. So consider x as variable and any other terms as constant. Means only x is variable in this question. Partial differentiation means only x is variable in this question. This y is constant for this partial differentiation. Okay, so this is the meaning of partial differentiation. Okay, so when there is full differentiation, not partial, like this dV by dr, okay, then we will consider all the variables are variables. Okay, so if we are differentiating with respect to x, suppose if I am differentiating dV by dx, this is not partial differentiation. Okay, so when I differentiate it, it will become 6xy minus y plus 2yz upon dx. Okay, so we will this thing will differentiate this potential value with respect to x, but y and z are also variable here. This will consider y and z also as variables. Okay, but in partial differentiation, this we are differentiating partially with respect to x. Okay, but these other variables y and z are considered as constants. Okay, only x will be considered as variable. This is the partial differentiation. Okay, so what is we are differentiating now? 6xy. So x is variable and 6y is considered as constant. So it will get out and dx by dx will be 1. Okay, next y is constant. So differentiation of a constant 0. So this term will result in 0. Y and z both are constant and 2 is constant. So this whole term is constant. So differentiation of a constant value is 0. Okay. So only 6y will be remained. Okay. Because x is present in this term. And this partial differentiation will only consider x as variable, other as constant. So 6y will be achieved. Okay. After that, del v by del y, partial differentiation with respect to y. Now, partial differentiation with respect to y, only y will be considered as variable and x and z will be considered as constants. Okay, so 6xy with respect to y, so it will become 6x after differentiating, minus y will become minus 1 because minus del y by del y, which will become 1, plus 2yz. So del 2yz upon del y, so 2z are constant, they will come out, and dy by del y 1. So 2z. Okay, so partial differentiation of potential with respect to y is 6x minus 1 plus 2z. Similarly for delta v, del v by del z, partial differentiation with respect to z. So this term is constant because z is not present, this term is constant, only this term has z. Okay, so it will become 2y. 2y will come out and del z by del z 1. So 2y will be the answer for this differentiation. Got it? Now put this all the values del v by del x at this point, del y by del z, del v by del y at this, and del v by del z at this. Okay, so this will become minus in bracket 6y I cap plus 6x minus 1 plus 2z j cap plus 2y k cap. Okay, now we have to find the electric field at this point 1 1 0, x equal to 1, y equal to 1, z equal to 0. Put y equal to 1, x equal to 1 and z equal to 0. After putting these values, we will get E at 110 is minus 6i cap, 5j cap plus 2k cap. Got it? Okay. A combination of capacitors is set up as shown in the figure. The magnitude of electric field due to point charge Q having a charge equal to sum of charges on 4 microfarad and 9 microfarad capacitors at a point distance 30 meter from it would equal. Okay, so we have to find the electric field due to a point charge Q at 30 meter from it. And what is the magnitude of this Q? The magnitude of this Q is the sum of charges on this 4 microfarad capacitor and this 9 microfarad capacitor. Okay, so why this circuit is given? Because the magnitude of that charge due to which electric field is to be found is this Q has the magnitude equal to the sum of the charges on this 4 microfarad capacitor and this 9 microfarad capacitor. Okay, so after finding the charge Q, we will find the electric field due to this charge at a distance 30 meter away from it. Okay, so the options are 420 Newton per coulomb, 480 Newton per coulomb, 240 Newton per coulomb, 360 Newton per coulomb. Okay, so I will give you some time. So the correct option is A, 420 Newton per Coulomb. So solution are, so this is the thing we are going to do. So we will find the equivalent capacitance of these capacitors that are in parallel combination. So equivalent capacitance will be, since they are in parallel, so it will be algebraic sum of both the capacitance. 9 plus 3, 12 microfarad is the CP, equivalent capacitance of parallel combination. Okay, so in figure, 3 microfarad and 9 microfarad are in parallel. Okay, so CP will be 3 plus 9, which is equal to 12 microfarad. Got it? So this combination is in series with 4 microfarad capacitor. Okay, so this combination 12 microfarad CP is in series combination with this 4 microfarad capacitor. Okay, so since they are in series, so for series combination 1 by CS, 1 by 12 plus 1 by 4 equal to 1 by 3. So in series combination, so the equivalent capacitance of series combination of these two capacitors C1 and this CP. Okay, further CP is the equivalent capacitance of these two parallel capacitors. Okay, so CS will be 3 microfarad. So equivalent capacitance of these three capacitors will be 3 microfarad. Okay, which is equal to CS. Okay, again same diagram. Now what is the charge in this section? Because we have find the equivalent capacitance between this section of this branch of the circuit, which is 3 microfarad. Now we can find the charge because potential difference across this branch, potential difference, since this 2 microfarad and this whole branch both are connected in parallel to this battery. So potential difference will be 8 volt across both the branches. So potential difference across this upper branch will be 8 volt, and equivalent capacitance of this branch is 3 microfarad. So charge will be CS into V, 3 microfarad into 8 volt will be 24 microcoulomb. So charge in this branch is 24 microcoulomb. Since charge in series remains same, so charge on this 4 microfarad will be 24 microcoulomb, and charge on this combination CP, combination of these two parallel capacitors, will also be 24 microcoulomb. But we have to find the charge on this 9 microfarad capacitor. Okay, so what we can do, voltage distributes itself in the inverse ratio of capacitors 4 microfarad and 12 microfarad combination of two capacitors. Okay, so since they are in series, okay, so potential 8 volt across this branch will be distributed in the inverse ratio of capacitors. Inverse ratio means the capacitor having less capacitance will having more voltage across it. The capacitor having more capacitance will be having less voltage across it. So inverse ratio. Okay, the voltage across CP. Now we have to find the voltage across CP. So we will take in the numerator capacitance of the other capacitor, because it is inverse ratio. If we want to find the voltage across this 12 microfarad capacitor, we have to take in numerator the capacitance of other capacitor and upon the sum of both the capacitances. Okay, so voltage across CP is VP, which is equal to 4 the capacitance of other capacitor upon the sum of both the capacitances. Okay, this is the term, this is the inverse ratio, into 8. What is 8? The total potential across this branch. Okay, so the potential across this 12 microfarad, which is the equivalent capacitance of both these capacitors, is equal to 2 volt. Got it? So 2 volt is the potential across this 12 microfarad, means across these two capacitors. Since they are in parallel, so potential difference across both the capacitors will be 2 volt. So voltage across 9 microfarad is also 2 volt. Got it? So charge on 9 microfarad capacitor will be now, we have found the voltage. Okay, we know the capacitance. So Q equal to CV. C is 9 microfarad, V is 2 volt. So charge on 9 microfarad capacitor is 18 microcoulomb. Okay, so now charge on 4 microcoulomb was 24 microcoulomb. 4 microfarad capacitor is 24 microcoulomb, and charge on 9 microfarad capacitor is 18 microcoulomb. Okay, now sum of the charges on both these capacitor will be total charge now Q charge on 9 microfarad capacitor plus charge on 4 microfarad capacitor, which is equal to 18 plus 24, 42 microcoulomb. Okay, now we will find the electric field at a distance 30 meter from this point charge, which is having magnitude 42 microcoulomb. So this Q is 42 microcoulomb. Okay, so KQ by R square, 9 into 10 to the power 9 into 42 into 10 to the power minus 6 upon 30 into 30, which is equal to 420 Newton per coulomb, which is the answer. Got it? Okay, next question. The diagram below show region of equipotentials. A positive charge is moved from A to B in each diagram. Okay, in all 4 cases, the work done is same. A option. B option, minimum work is required to move Q in figure. Okay, maximum work is required to move Q in the figure 2. Maximum work is required to move Q in the figure 3. So we have to determine that. Okay, so since this A and B point, okay, so we have to move the positive charge from A to B. I will give you some time to think about it. So option A, in all the 4 cases, work done is same. Why? Work done is equal to Q into potential difference. Okay, so positive charge is moved. So positive charge is same in all the cases. Potential difference. Now you can see this B point is at 40 volt in all the diagrams. This B point is at 40 volt in all the diagrams, and A point is at 10 volt in all the diagrams. So potential difference in all the cases is 30 volt. Okay, so since potential difference and magnitude of positive charge is same in all the cases, so work done is same in all the cases. Okay, so what is the solution? As the regions are of equipotentials, so work is Q into delta V. So delta V is same for all the cases, which is 40 minus 10, 30 volt. Hence work done will also be same in all the cases. Got it? Simple. So our next question, a capacitor is charged by a battery is removed and another identical uncharged capacitor is connected in parallel. The total electrostatic energy of resulting system is, okay, so firstly we charged a capacitor with a battery, then we remove the battery and another uncharged identical capacitor is connected in parallel. Okay, the total electrostatic potential energy in the resulting system we have to calculate. Okay, so options are decreased by a factor of 2. It means the final energy is decreased by the initial by the factor of 2 as compared to initial energy, or remains the same, or increase by a factor of 2, or increase by a factor of 4. Okay, so I will give you some time. So let's see what is the correct option. A option, decrease by the factor of 2. Let's see the solution. Charge on the capacitor initially is given, what is the charge? Q equal to CV. Charge is equal to C, which is the capacitance of the capacitor, into the battery with which it is charged. having potential V. Okay, where Q is the charge stored, V is the potential difference across its plate, C is the capacitance of the capacitor. Energy stored initially in the capacitor is calculated using the formula half CV square. Okay, so initial energy is half CV square. Now, it is connected like this. This is the charged capacitor. This is the uncharged capacitor. So uncharged capacitor is connected in series, in parallel with this charged capacitor. And both the capacitors are identical. Means their capacitances are same. So like these are connected in parallel. So one plate, positive plate is connected with positive plate of other, negative plate is connected with negative plate of other. Okay, so they will attain some common potential. Okay, charges will start flowing from this capacitor to this capacitor. After redistribution of the charges in static condition, when there is no flow of charges, these both capacitor will attain same potential known as common potential. Okay, since they are in parallel, so they will be at same potential known as common potential. So what is the common potential? When charged capacitor is connected with another identical uncharged capacitor, common potential is given by Vc equal to Q1 plus Q2 total charge upon total capacitance. Okay, sum of capacitances, which is equal to Q1 charge. Initially charge on first capacitor is Q, or charge on second capacitor initially was 0. Capacitances of both the capacitor are C. So Q by 2C, and Q by C is V. Q by C is V initially when one capacitor was there, Q equal to CV, and V was Q by C. So this Q by C will be V, initial V, potential of battery. So common potential will be V by 2. Okay, so V was the initial potential on this capacitor. V common is V by 2. Okay. Final energy of the combination of two capacitors is now given by. So final energy UF, final energy is half C V by 2 square. It is the energy of one capacitor plus energy of second capacitor. Since they are at common potential and their capacitances are same, so half C V by 2 square, half C V by 2 square. So this will result in CV square by 4. Initial energy was CV square by 2. So it is decreased by a factor of 2. So loss in energy, what is loss in energy? Ui minus Uf. So loss in energy is also CV square by 4. Final energy is also CV square by 4. Initial energy was CV square by 2. So final energy, electrostatic energy of the resulting system is decreased by factor of 2. So it decreases by a factor of 2. Okay, initial energy was CV square by 2. Final energy is CV square by 4. Loss in energy is CV square by 4. Okay, so since initial energy was CV square by 2, so it is decreased by a factor of 2. Next question, electrostatic force between the metal plates of an isolated parallel plate capacitor C having a charge Q and area is. Okay, so what is the electrostatic force between the metal plates, okay, of an isolated parallel plate capacitor having charge Q and area is independent of the distance between the plates. So the electrostatic force between the metal plates of the isolated parallel plate capacitor is independent of distance between the plates, or linearly proportional to the distance between the plates, or inversely proportional to the distance between the plates, or proportional to the square root of distance between the plates. So I will give you some time to think about it. So answer is A, independent of the distance between the plates. Okay, so how? Let's see the solution. So electric field E due to any one plate of the parallel plate capacitor can be calculated using the formula. Okay, so electric field E due to any one plate, negative plate or positive plate of the capacitor, can be calculated as, so due to one plate it is sigma by 2 epsilon naught. But net electric field between the plates of capacitor is sigma by epsilon naught, which is the sum of electric field of both the plates. But we are only considering electric field due to any one plate of the capacitor. Okay, so that is sigma by 2 epsilon naught. Therefore, electric field E becomes equal to Q by sigma is surface charge density, that is Q by A, area of the plate, charge on the plate. So Q by 2A epsilon naught. Now force F on one plate due to electric field created by another plate. So one plate, electric field due to one plate, and due to this electric field, other plate will experience some force. Okay, so this is electric field produced by one plate, and due to this electric field, other plate which is also charged will feel some force which is equal to Q into E. Okay, so force F on one plate due to electric field created by other plate. Okay, so force on one plate due to electric field created by other plate can be calculated using formula force equal to Q into E. Okay, so one plate is applying force on second plate. That is the electrostatic force between the metal plates. Okay, we don't have to consider the opposite force also. That is, other plate is applying on another plate. It will be, both plates are applying force, na? But this is Newton's third law, na? These forces are equal and opposite. Okay, so we only consider one force. Force on one plate due to another plate. That will be the force between the metal plates. That other force that another plate is applying is reaction force. Substituting the expression for E, so E will become Q into E. So E is Q by 2A epsilon naught, which will become Q square by 2A epsilon naught is the answer. Okay, so electrostatic force between the metal plates is, which is between the metal plates, is Q square by 2A epsilon naught. Okay, for isolated capacitor Q is constant. Since Q is constant, area of the plates is constant, epsilon naught and 2 is also constant. Okay, so the force is independent of the distance between the plates. Okay, there is nowhere separation, distance of separation between the plates is given. So force is independent of the distance between the plates. So next question, a short dipole has a dipole moment of 16 Newton per minus 9 coulomb meter. The electric potential due to dipole at a point at a distance of 0.6 meter from the center of the dipole situated on a line making an angle of 60 degree with the dipole axis. Okay, there is a short dipole having dipole moment 16 Newton per minus 9 coulomb meter. The electric potential due to dipole at a point of distance 0.6 meter from the center of the dipole. Okay, so this is the distance from the center of the dipole where we have to find the electric potential situated at the line making an angle 60 degree. So that line, that position vector from the middle of the dipole to that point is at 60 degree with the dipole axis. And 1 by 4 pi epsilon naught value is given 10 in 9 into 10 is per 9 Newton meter square per coulomb square. Options are 200 volt, 400 volt, 0 and 50 volt. I will give you some time to think about it. So the correct option is A, 200 volt. Solution is, so dipole moment for a short dipole is given P equal to 16 10 per minus 9 coulomb meter. Distance of a point from center of the dipole R is equal to 0.6 meter. Electric potential at a point due to short dipole is given by V equal to K P cos theta by R square. This is the potential at a point due to short dipole. Okay, where P is the dipole moment, theta is the angle between the dipole axis and the line joining that point with the center, okay, of the dipole, and R is the distance of that point from the center of the dipole. Okay, so after substituting the values P of P cos theta, which is 60 degree, and this constant K, which is 9 into 10 to the power 9, P is 16 into 10 to the power minus 9, and this R is 0.6. R square is 0.6 into 6. After substituting the value and solving, we will get 200 volt. Okay. Our next question is, capacitance of a parallel plate capacitor with air as medium is 6 microfarad. With the introduction of a dielectric medium, the capacitance becomes 30 microfarad. The permittivity of the medium is epsilon naught 8.85 into 10 to the power minus 12 coulomb square per Newton meter square. Okay, so there is a parallel plate capacitor with air as medium, which is 6 microfarad. Then there is a dielectric medium inserted between the plates of the parallel plate capacitor. Then its capacitance becomes 30 microfarad. Permittivity of the medium is given. Okay, so your options are 1.77 into 10 to the power minus 12 coulomb square per Newton meter square, 0.44 into 10 to the power minus 10 coulomb square per Newton meter square, 5 coulomb square per Newton meter square, or 0.44 into 10 to the power minus 13 coulomb square per Newton meter square. So I will give you some time to think about it. So let's see the correct option. Correct option is B. 0.44 into 10 to the power minus 10 coulomb square per Newton meter square. So let's see the solution. Capacitance of a parallel plate capacitor with air is C equal to epsilon naught A upon D. Okay, so when there is a air between the parallel plates of the capacitor, then capacitance is given by epsilon naught A upon D. Mark it as equation 1. Here A is equal to area of the plates of the capacitor and D is distance between the plates. Capacitance of same parallel plate capacitor with introduction of dielectric medium. Okay, when we insert the dielectric medium within its plates, then of dielectric constant K, then the capacitance is given by C dash K epsilon naught A upon D. Mark it as equation 2. Okay, so now we will see what is K, what is permittivity of the medium. So permittivity of the medium is, what is permittivity of the medium? This is permittivity of free space, epsilon naught. Permittivity of medium is epsilon, and epsilon is given by epsilon naught epsilon r. Okay, so this is permittivity of medium, this is permittivity of free space, and this is permittivity, relative permittivity. Okay, so dielectric constant is equal to the relative permittivity. Okay. So now dividing 2 by 1, C dash by C equal to K. Okay, so after dividing 2 by 1, so we will get K. So K is equal to C dash by C. What was C dash? 30 microfarad when dielectric plate is inserted between its plates. And 6 is capacitance of a parallel plate capacitor with air as medium. Okay, so dielectric constant will come out to be 5. Now K is also known as relative permittivity. Okay, and it can be also shown in the form of ratio of permittivity of medium to the permittivity of free space. Okay, we have discussed in electric field chapter. Okay, so what is permittivity of medium? Permittivity of medium equal to K into epsilon naught, permittivity of free space. Okay, equal to 5 into 8.85 into 10 to the power minus 12, which will result in 0.44 into 10 to the power minus 10 coulomb square per Newton meter square. Got it? Okay, let's move on to the next question. A dipole is placed in an electric field as shown. In which direction will it move? Okay, so this is the dipole. This is dipole plus this is negative charge, this is positive charge. So dipole moment is in the direction of negative to positive charge, and this is the direction of electric field. This electric field is non-uniform. This is the source from where it is producing. Okay, but this dipole is along this electric field line. Okay, So you have to tell, these are the four options. Towards the right, in which direction will it move? Towards the right, as its potential energy will increase. Towards the left, as its potential energy will increase. Towards the right, as its potential energy will decrease. And towards the left, as its potential energy will decrease. Okay, so these are the four options. So I will give you some time to think about it. So correct option is C, towards the right, as its potential energy will decrease. Okay, so let's see the solution. So this is the diagram. Okay, so now dipole moment is in the direction from negative to positive charge, and electric field is in this direction. Okay, both are at an angle of 180 degree. So angle between this dipole moment and this electric field is 180 degree. Okay, so they are anti-parallel. Okay, now we will see what is potential energy of electric dipole in an external field. When dipole is placed in external field, what is the potential energy? Minus P dot E. P is dipole moment, E is electric field. Okay, potential energy is given by minus P dot E, which is minus PE cos theta. Theta here is 180 degree. And cos 180 degree is minus 1. So it will result in U equal to, since angle between E and P is 180 degree, so U is equal to plus PE. Okay, so now you can see where dipole will move. Okay, so we know that electric field is in this direction. Okay, and this is not uniform electric field which will remain constant. This is non-uniform electric field, and this is source from where it is producing. So it will keep on decreasing as we move away from the source. Since electric field is decreasing as we move away from the source, then if we move this dipole away from or move in the right direction, so electric field is decreasing, it means potential energy will also decrease. Okay, so let's see again diagram. On moving towards right, electric field strength decreases. Okay, because the electric field is inversely proportional to r square for a point charge. It is a point source, na? Electric field produced due to point source. So electric field is inversely proportional to r square. Okay, so electric field will decrease as we move away from this point charge. Since electric field is decreasing, so potential energy will also decrease. So U decreases. Okay, now in which direction it will move? It will move in this direction, in the direction of electric field, because its potential energy is decreasing in this direction. Also you can see this is positive charge, here is source charge. Okay, so this positive charge will feel, this is also positive charge because this source charge is also positive because electric field is radially outwards. So this positive charge is near this positive charge, so this will experience force in this direction. This negative charge will experience force in this direction. Also we can say this positive charge experience force in the direction of electric field, and this negative charge will experience force in the direction opposite to the electric field. Since this positive charge is near to that source, it will experience more force than the force on negative charge. Okay, so this positive charge will experience more force than the negative charge. So net force is in the direction of electric field. Okay, so it will move in the direction of electric field. This dipole as whole move in the direction of electric field. Also U is decreasing in this direction, so it will move in this direction. So what about the torque? Is it any torque applying on it? Okay, what is torque? PE sine theta. Okay, theta here is 180 degree. Sine 180 degree is 0. So no torque is being applied on this dipole. So in which condition this dipole lies? In unstable equilibrium. Okay, in unstable equilibrium. We know that what is stable equilibrium? If dipole moment is in the direction of electric field, that is stable equilibrium. But if it is anti-parallel to electric field, then it is unstable equilibrium. Means no torque is applying, but the equilibrium is unstable. If we rotate it through small displacement, small angular displacement we will give, it will rotate and align in the direction of electric field. Means it is not in the stable equilibrium. Got it? Net force on the electric dipole is towards right, and net torque acting on it is 0. So move towards right. I hope you understood it. Now the equivalent capacitance of the combination shown in the figure. So you have to tell the equivalent capacitance of this combination. Your options are 3C by 2, 3C, 2C and C by 2. Okay. I will give you some time. So correct option is C, 2C. Okay. So let's see the solution. The circuit is as shown in the figure. So let's see this circuit. Okay. Now you can see that this capacitor is connected between these 2 points, 1 and 3. Okay. So this is the simple wire of the circuit. Okay. Now we know that if this capacitor block the current, okay, so these will block the current, so we will not consider current here. Okay, if there were resistors in this place, we would say that this is the wire with negligible resistance, so current will prefer to flow through that path and will not flow through that path. Okay, but now there is a capacitors, they block current in the steady state, so we will not deal with the current here, we will deal with the potential difference. Okay, since this wire is connected in parallel to this capacitor, okay, so potential difference on these 2 points will be same. Okay, so since the potential difference potential on these 2 points is same, potential at 1 and potential at 3 is same, so potential difference will be 0 between these 2 points. Okay, since potential difference is 0, then Q is equal to CV. If potential difference is 0, charge stored will be 0. Okay, points 1, 2 and 3 are connected by a conducting wire, so these points are at same points. These 3 points, 2, 1 and 3, because they are connected by a conducting wire, so all these 3 points will be at same potential. Since they are at same potential, so potential difference between these points is 0. So potential difference between 1 and 3 is 0. So no charges will be stored on this capacitor. So this will not be considered in the circuit. Okay, so there are only 2 capacitors that are storing charges and they are connected in now parallel. One is at one plate of both the capacitor at A point and another plate of both the capacitor is connected at B point. Okay, so they are in parallel, so equivalent capacitance will be, so the capacitor is short circuited. This condition is called short circuited, when potential difference across the terminals of the capacitor is 0 and charges stored on the capacitor is also 0. So it does not store any charge. Therefore equivalent capacitance is due to these 2 capacitors connected in parallel, that is C plus C, 2C. Got it? A capacitor of capacitance C equal to 900 picofarad is charged fully by a 100 volt battery. Okay, so one capacitor, this of capacitance 900 picofarad, is connected with 100 volt battery B as shown in the figure. Then it is disconnected from the battery, and connected to another uncharged capacitor. This is uncharged capacitor initially. Okay, of same capacitance 900 picofarad as shown in the figure B. The electrostatic energy stored by the system is, now electrostatic energy stored by the system B is, this is the B system, now electrostatic energy stored by the B system is given by, okay, so now this is connected in parallel to this capacitor, so charges will start flowing from this capacitor to this capacitor. Okay, so in steady state, when there is a distribution of charges and when flow of charge becomes steady, okay, then these 2 capacitors will attain some same potential because they are connected in parallel, that is known as common potential. Okay, so now we will see options are 3.25 into 10 to the power minus 6 joule, 2.25 into 10 to the power minus 6 joule, 1.5 into 10 to the power minus 6 joule, and 4.5 into 10 to the power minus 6 joule. I will give you some time to think about it. So answer is, correct option is B, 2.25 into 10 to the power minus 6 joule. How? We will see. Okay, so by conservation of charge, charge will remain same before the charge in the circuit will remain same before the connection and after the connection. Okay, so Q initial will be equal to Q final, which is given by, what is Q initial when it is connected to battery of 100 volt? CV, Q equal to CV. So C into what is the potential difference? 100 initially. And what was the final charge? Equal to CV dash. What is CV V dash? V dash is common potential. Okay, so common potential, what is common potential? I have already mentioned that when we connected this uncharged capacitor with this charged capacitor, there is a flow of charges, and flow of charges continues till both the capacitor will attain a same potential difference across their terminals. That is called common potential. So charge on this capacitor is CV dash, and charge on this capacitor is also CV dash, equal to V dash is given by 50 volt. So common potential is 50 volt after the connection, where V dash is the common potential after distribution of charges. Okay, so final energy will be the sum of individual energies on both the capacitors at common potential. Okay, final energy is given by the individual energies on both the capacitors at common potential. Okay, so final energy is given by half C V dash square. This is the energy on this capacitor, and half CV square. This is the energy on this capacitor. Okay, since their capacitances are same, 900 picofarad, which is results into CV dash square. Okay, now put the value of C, which is 900 picofarad, into 10 to the power minus 12, 900 into 10 to the power minus 12, into what is the common potential? 50. 50 square is 2500. 25 into 10 to the power 2. So it will result in 225 into 10 to the power minus 8. And the answer is 2.25 into 10 to the power minus 6 joule. Okay. So thank you. I hope you understood and enjoyed the session.